see if this will work. Hopefully this does. What we're going to talk about is cleavage and fracture. So cleavage is always the tendency of a mineral to split along planes, surfaces. And of all of them, probably the easiest to see that with is mica. Mica is very easily split along cleavage planes, and you can see that if I take a blade and I slide it in, you can see that it separates along those planes. And in fact, this is so good that I can continue to, down to the microscopic level, continue to split mica. Mica is considered to have a one-way perfect cleavage. In fact, when it's rated, it gets a value number of 1 because this indicates the number of planes of cleavage. And then it gets 3 pluses, which is kind of like on a scale of 1 to 3, how good is it? So this is the quality. So mica has a single plane of cleavage. I can't split it going vertically in either direction. It only splits along this flat plane. So it gets 1 plane, and it's considered to be the top of it. So it gets 3 pluses. That's usually the value that is assigned. Biotite mica and muscovite mica are both the same in terms of that. Now, this is gypsum, and I have a relatively thin piece right here, but if I can take my blade and press down, you'll see that it penetrates right in, and it will split along that same plane of cleavage, and I can separate it down into, multiple layers. Now, you'll see that the surface is very reflective, and it is fairly smooth. The drawback to gypsum in terms of the way that it cleaves is it does not cleave as perfectly as mica does. So although this does split pretty nicely along that single plane of cleavage, mica will oftentimes get a value that looks like this, 1 with 2 pluses. So it's got 1 plane of cleavage that's very good, but it isn't excellent as compared to mica. All right. Let me show you another one. This is halite, and halite has 3 planes of cleavage. So if I take my blade and I set it on top of here and I give it a good tap, you'll see that it splits vertically. If I set it on its side, it splits horizontally, and if I rotate it 90 degrees, it splits on that plane as well. So you can see that the surfaces are very, very shiny, reflective. I would even argue that this is as close to a perfect cleavage on 3 different planes as you're going to get. So this one would get, instead of a 1 with 3 pluses, because halite splits on 3 different planes, it gets a number of 3 because it's 3 different planes of cleavage, and it would get 3 pluses because those planes of cleavage are very, 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 very smooth. And when you think about it from a 3-dimensional point of view, right, I have my vertical plane of cleavage, I have my horizontal plane of cleavage, and I have my depth plane of cleavage. And on each one of those 3 axes, I'm able to get that to cleave. So halite has 3 planes of cleavage. All right. Now, another one that's very similar to that is this one. This is calcite, and if I take calcite and I hit it with a hammer, this one actually will fracture into a lot of little pieces, break into a lot of little pieces. But even the smallest of the pieces that break off all exhibit that rhombic structure. This has 3 planes of cleavage. So I have one plane of cleavage, a vertical plane of cleavage, and a second vertical plane of cleavage. And I would argue that these are pretty smooth surfaces. It doesn't always split as cleanly, so sometimes you'll see calcite being given a value like this, 3 with 2 pluses. So it has 3 planes of cleavage, not as good as perhaps halite. It takes a little bit more work to get it to crack, but you can get it to break. Now, there are some that only have, let's say, 2 planes of cleavage. And this is feldspar. This is sodium feldspar. Sodium feldspar actually has 2 planes of cleavage, and you can see that first plane here with this smooth surface, and you can see that there's a second plane of cleavage along here. But this surface is rough. So this one would get a 2, and it's reasonable. It's not fantastic, but it's a reasonable plane of cleavage. Usually I've seen it as 2 with 2 pluses or 2 with even just 1 plus. And if we were to take this one and we were to hit it hard enough with the mallet, you can see it's a very, very tenacious material. It does not cleave easily. So even if I were to pound on this with a chisel, I would still be able to get it to crack along those planes, but it really does require a tremendous amount of energy and effort to get it to cleave. So this is one of them that's kind of a weird one, but it does have 2 planes of cleavage. This is a really odd one. This is fluorite. Fluorite actually exhibits 4-way cleavage. So I actually have got a plane of cleavage that goes like so. I have another plane of cleavage that goes like so. I have another plane of cleavage that runs like so. And I have another plane of cleavage that runs like so. So this one actually has 4 different planes of cleavage. The samples that we have are really difficult because many of the crystals have actually grown into one another. And as a result, it doesn't break cleanly as easily as some of the other samples. This is a smaller piece. I'll see if I can get it to cleave. Boy. There you can see that it split real cleanly on that plane. So there's one of the surfaces. You can see the other surface here, really smooth, and you can see some other surfaces here and on this surface too. So this one does, if you hit it well enough, you can actually get it to show those 4 planes of cleavage. This one actually shows it really well. It forms almost like a little tetrahedron. So there are 3 planes of cleavage from this point, 1, 2, and 3, and then there's 1 plane that goes across the bottom. So fluorite is one of those that gets 4 planes of cleavage. All right. Now cleavage is usually easy to see because it's going to have a flat surface. Now that's not always the case. If we take a look at, let's say, a a crystal of quartz, you might have a crystalline shape to it, but those surfaces are not what we consider to actually be cleavage planes. If you were to hammer on a piece of quartz, it would shatter into curved surfaces. This one, which is garnet, does not exhibit cleavage. What it exhibits is instead fracture. So if it does not have cleavage, it has fracture. So this one has a very, very chipped surface, and in fact, if you get it in the right light, you can see that those chips are slightly curved. This is a piece of milky quartz. It too does the exact same thing, and you can see in the glinting off of the light, you can see that there are these curved surfaces that are left behind. This type of fracture, not cleavage, this type of fracture has a name, and we call it conchoidal. Conchoidal fracture. So conchoidal fracture is where you get almost like a curved chip, and you'll oftentimes see sometimes little concentric rings that are by that surface, but that surface has actually got this chipped edge. That chipped relief, typically seen in like glass, is called conchoidal fracture. So conchoidal is one that's a fairly common type of a fracture. Other types of fracture are more like hacky fracture. Let me see if I've got a piece that will exhibit that. So this is actually a piece of calcite, but there are some sections on here that show what we refer to as a hacky fracture. The fracture surface is more irregular. It's not real even. If you remember from looking at some of the samples that we had in back, limonite and most of the iron ores. This is magnetite, right? And this is hematite. All right. No flat, clear, broken surface. These are all just real rough, and we just call it hacky. That's probably the best way to describe it. This rough appearance, the same on this one. There's no clean plane. This is just considered to be hacky fracture. So in this case, we would refer to it as HACKY, hacky fracture. A lot of them are going to either be conchoidal or they're going to be hacky. It's tricky to tell the difference between when you have a crystal that has a shape versus we're actually looking at something that has a cleavage plane. So one of the samples that you have forms these hexagonal prisms. Can you guys tell me what mineral it is that has that shape? Quartz definitely is one of them. There's another one that forms these little prisms, these little hexagonal cylinders. You can look at your sheets, by all means. You're going to need to be able to identify these things. Look at your sheets. You'll find it. It's in there. It's dark purple, although underneath the UV lights it actually glows almost a red. Corundum. Now, if you hit corundum, corundum is actually going to shatter and fracture. It will produce the conchoidal chips. So although you see it in this kind of tabular form, this cylindrical prismatic form, that form is not its cleavage planes. The same with quartz. If you hit quartz, it will shatter and chip, and it will show conchoidal fracture. So I'm going to come around, we'll go through the examples that we have, and you can kind of get a little bit of an understanding of how those come together. Right? Questions? Okay. Let's go through one last one, and that is variations of crystal habit. So we've all taken a look at pyrite, and we've seen pyrite in its massive forms. Whenever we have a mineral that's in what we refer to as a massive form, it doesn't have a specific shape to it. This piece is actually a piece of pyrite that we would refer to as being massive. Its crystal form is not perfect in terms of a cube or an octahedron or a tetrahedron. It's just a big chunk. Sometimes we find pyrite in a crystalline matrix where the little crystals have all grown into one another. And in fact, this one, if I can get it to focus, if you look really closely at the various pieces, you will see in some cases little tiny cubes, like right here at the tip of my fingernail. But you may also find other pieces that are more dodecahedral, that they'll have more like a 12-sided form. And the surfaces are actually made of little pentagons. And in fact, you can see one right here at the tip of the pencil, tucked in, right there. See that little 5-sided crystal? There's a little pentagon right there. Okay? So this one is an interlaced sample with lots of different crystals that are all blended together and grown together. This one shows the dodecahedral ones. Notice that the surface here is 5-sided, and it's growing into another one that is also 5-sided, and into another one that's a partial crystal that's grown 5-sided, and here's another one. So this one is a classic example of a dodecahedral arrangement to the crystals, but they have twinned together, they've grown together. So that's another form that we see with pyrite. This is kind of cool because instead of having a 5-sided piece, it has a 3-sided. It's got triangular facets, and it actually is octahedral. So this is another form of pyrite. It still is pyrite, but it has a very, very different octahedral base. And you guys, you actually created these little octahedrons in cardboard, but you can see another one here. It's grown into this one. We refer to that as twinning. This is another piece that we consider to be just massive. There are no clean, clear, flat surfaces to the crystals. The crystals are almost reniform or globular, lumped together. This is not uncommon with pyrite. This is another one that's got multiple forms. This one actually has a truncated octahedron, so there are some surfaces that are square, and then there are some surfaces that are triangular. This one is one of my favorites. This is a pyrite sun, and we don't see the individual crystals, but we do see what the effect is. The crystals are actually needle-like, and they grow out in all directions. The cool thing is, it's relatively flat, and it forms in between layers of sedimentary rock. These are typically found only in one area down in Illinois, and they're referred to as pyrite suns because they look kind of like a sun radiating its rays in all different directions. Sometimes they are really, really sparkly. This one has oxidized over the years. When I first got it, it gleamed like gold. It was really, 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 really bright. You can still see some of that effect right in here. But this is very unusual. We don't see this form very frequently. And then this is the last one, and possibly my favorite. Pyrite will grow in the shape of cubes, and the cubes will sometimes twin together. So what you see here is two pyrite cubes that grew into one another. I used to hand these around, and then somebody dropped it and it fractured, so I had to glue it back together. But you can still see the general cubic shape of it. All right, questions? Okay, so that's it for me for right now. What I'm going to do is I'm going to have you guys go back. We're going to work through fracture, and we're going to work through cleavage. When in doubt, my guess is usually, from a personal point of view, I usually will go the route if it's a fracture surface, particularly if you're not seeing a real clean, flat line. So with that, let me close off our record.